Position, velocity, and acceleration. Recall that position is typically modeled by s of t, and then velocity v of t, and of course acceleration a of t. Now, some facts to remember. Remember that d dt, the derivative of position, gives us velocity. Remember, the derivative of velocity gives us acceleration, and then vice versa. Recall that the integral of acceleration, the antiderivative, if you want to look at it like that, of acceleration would give you velocity with some potential initial constant velocity. And finally, recall that the antiderivative or the integral of velocity is going to give us our position plus some potential initial position. So from here to here to here, derivative. From here back, we find antiderivatives. We have initial height and we have initial velocity. Find the position height model. So the goal is to find position. In other words, the goal is to find s of t equals stuff. That's the goal. That's what we want to get to. But what do we have to begin with? There's one thing we have that's not written here, and that is this. Look, check it out. See this pen? It's falling because of gravity. And we have a gravitational constant. For this problem, our acceleration is going to be negative 32 feet per square second. And that's universal. If we're using feet, then automatically the gravitational constant, which is acceleration, would always be negative 32. If you were doing a math problem and they used meters instead, I believe it would be like negative 9.8. But for us, because they said feet, we're using this version instead of this version, where they both represent acceleration. But this is with metric units, and this is like what, standard units, like American units, I guess. So we're using negative 32 always. If they say feet, negative 32 is always your acceleration, unless they say something else. But if it's not directly given, this is our acceleration. Now, remember that the integral of acceleration, right, the antiderivative of acceleration is velocity plus some initial velocity constant. And that's what we want. So we know our acceleration is this. So the integral of negative 32 dt, well, what's the antiderivative of negative 32? It'd be negative 32t plus some initial velocity constant, which they said was 64. So this is negative 32t plus 64. So this is our velocity equation, our velocity model. But we want position. So to go from velocity to position, you do another integral. So now we're going to integrate velocity because we know it's going to tell us position plus initial position. So we have integral of velocity, which was this one here, negative 32t plus 64 dt. So let's see, the antiderivative of, let me cover that up with my finger. The antiderivative of t is 1/2 t squared. But there's a negative 32 that we must respect, so it just transfers through. The antiderivative of a 64 is 64t. And we know that the initial position was 80 feet of height. So that's negative 16. And so they asked for a position model, S of t. There it is.